Hi everyone, so I'm gonna try to quickly re-record the lecture I gave yesterday as well as I can. It's gonna be extra great because oh, he's gone. Well, I had a kitty helping me, we'll see if he comes back. Um, but this was our lecture focused on the heating and cooling processes, excuse me, within the ISM, as well as starting to think about some of the thermal and pressure equilibrium within the ISM. Sorry. So just to get started, we started with this image here, which is the Lundmark's image of the Milky Way. So this was something I wanted to start with because it reminded me a bit about how we ended class last week, looking at the multi-wave like Milky Way. The really amazing thing about this image is it's not a photograph, it's actually hand drawn. So there are 7,000 hand drawn stars that Lundmark drew on this image. So just really impressive what people were doing before there were cameras, and like you can see the large and small Magellanic clouds down here and just the band in the Milky Way, which weren't individual stars but a dust band that he drew in. So anyways, just something I thought was cool and wanted to share. The next thing we looked at was, again, just to review, I wanted to remind everyone of the different phases of the ISM. So this is from a book by Fabian Walter. He splits up his phases of the ISM slightly differently than I did. So there's some differences, but just as a reminder, we have our giant molecular clouds that are really dense. They don't take up much of the volume. Their filling factor is very low, but they take up a good portion of the mass, at about 20% of the mass in the ISM. So this is just the gas mass in the galaxies. It's not including stars. We then have, let's see, we then have the cold neutral and the warm neutral medium. The cold neutral is going to be the more diffuse gas, and then the lower densities, low temperatures. The warm neutral is going to be the PDR layers that we talked about last Tuesday. Sorry. And again, we're getting larger filling factors, but we're going down in density, up in temperature, down in density, and more filling factors as we go towards warmer phases. So they expand more, so we get to pressure equilibrium, but there's just moving faster. So they take up more of the volume despite being less of the mass. So then Fabian Walter does not split his warm ionized medium into two. This is where we differ. But it's the same kind of idea. So warm ionized, that means our hydrogen is all or mostly ionized. I split it up into two components, the diffuse and the H2 regions. We're at really low densities, really high temperatures, and then about 20% of the volume in the ISM and about 10% of the mass. And this is the diffuse ionized gas, and then the H2 regions are the H2 regions around star formation, areas of star formation, which we talked about also earlier in the semester. Oh, something scary happened. Okay, sorry. That's why I don't teach from home. The last phase is in the hot ionized medium. So this is that coronal gas, fills up a ton of space in the ISM, but is not much of the mass. So very hot, very, very low densities, mostly stuff in the halo of the ISM. So that's my little bit of review from last class. Now we're going to move into some new stuff, thinking about our equilibrium conditions. So the first equilibrium condition, we're going to focus on two: pressure equilibrium and thermal equilibrium. Pressure equilibrium we're going to look at just fairly quickly and simply. Sorry, trying to get myself organized here a little better. So the pressure equilibrium is just what keeps the phases of the ISM from expanding into each other. But not all of the phases are really in pressure equilibrium. So the giant molecular clouds with molecular medium, the cold molecular medium, is not necessarily going to be in pressure equilibrium because it's actually dense enough that it will be gravitationally stable and hold itself together through gravitation instead of needing that kind of pressure from the thermal pressure to stay to keep from collapsing or to expand into the other phases. The other phase that's not necessarily going to be in pressure equilibrium is the coronal gas, so that hot ionized medium. It's expanding into the other phases, so it's like constantly expanding into the other phases, so we can't really say it's in pressure equilibrium. But the warm ionized, both the diffuse and the H2 regions, as well as the 2 atomic phases, are in pressure equilibrium. So some of our ISM is maybe about half. 4 of my 6 phases and about 50% of the filling factor are in that pressure equilibrium. And we can use the ideal gas law to model this. So PV equals nRT is our ideal gas law. So we're saying we're in pressure equilibrium, so our pressures are equal. Thinking about volumes a little bit more confusing, but what we can do is we can instead write the left-hand sides of our equations, put them together. So NKT equals NKT if we are in pressure equilibrium. K is a constant, so it's not going to change based on phase. We can divide that out and end up with just NT will equal NT for the different phases. So if we're looking at the boundary of the ionized and atomic, we can rewrite this equation like this, where in the ionized, our density is going to be from ionized hydrogen, so electrons and protons. For the most part, there will be a little bit of helium and then some metals, but this is going to be most of our density. And then the temperature of the ionized phases should be approximately equal to the number density of hydrogen in the atomic phases times the temperature. Now this is all pretty hand wavy because there's a lot of other kinds of pressures that I'm not including here. So there's also magnetic pressure from the galactic magnetic field lines, as well as from pulsars and other objects that might have magnetic fields. There's radiation pressure from stars, as well as from the CMB radiation, so the cosmic microwave background radiation. And then there's also going to be some ram pressure from gas clouds moving together. So thermal, like this kind of ideal gas law pressure, thermal pressure, part of the picture, but it's not the whole picture. And we're going to stay here though, because putting magnetic fields into anything gets too complicated too quickly. So this is what we're going to focus on in terms of pressure equilibrium, which is to say that NT equals NT should be true for the different phases, or should be approximately true for the different phases. Okay, so this was a question I asked the class. Let's see, some of our answers are going to pop up here. Cool. So what we decided was that temperature is probably going to be related to the motion of particles in a thermal system. And then there's also a possibility that there might be a definition related to black body radiation. So that's exactly what I was hoping to see. So motion or vibration of particles kind of related to pressure, energy of particles, but then also we might want to define pressure based on black body, or temperature based on a black body radiation. And that's exactly what we're going to do. So we're going to focus on 2 temperatures in the ISM. These are 2 distinct temperatures. It's not different between phases, it's different between the materials we are looking at. So we're going to think about a dust temperature and a gas temperature. So the dust temperature is the temperature of a black body. Approximately, dust isn't quite a black body, but it's going to be pretty close to a black body temperature of the dust. So this is going to typically be between 10 and 200 Kelvin, and we can calculate it using this equation here. There's a derivation I put online that I realized I do not have ready to do. Let me do my best. So I'm gonna stop sharing and instead go to a whiteboard. So if we have a kind of spherical dust grain with a radius of A, and it is a distance D from a star, that has a luminosity L star, we can figure out the temperature of this dust grain from absorbing light from this star. This is similar to something you might do in planetary science when you're looking at the temperature of a planet. So that's in your mind. So what we want to find is we want to find the flux that this dust grain absorbs, And then we're going to set that equal to the amount of energy that the dust grain emits. So we're going to say the energy the dust grain absorbs is going to be equal to what it emits, and we're going to use that to find a temperature. So that's going to look like P absorbed, so the energy the dust grain absorbs should equal P emit. PEM is what I'm going to call that. So the flux, first thing we need to think about is the flux from the star at the dust grain. So using inverse square law and just kind of the definition of flux, we can write the flux from the star at a distance of d is going to equal L star divided by 4 pi d squared. I think I might have put a sigma in there. I'll send a message out about this, but I think I might have put a sigma in there that I did not mean to put in. So there should not be a sigma there, I think. Now we want to think about how much of that energy is going to get absorbed. So we have to pretend that this is a nice sphere. Actually, I can't really draw that. So this dust, the surface of the dust that sees starlight is a circle, just a flat circle with a radius of a. So it's going to absorb this flux over an area of pi a squared. So just the surface of a circle with radius a. So P absorbed is going to be equal to the flux from the star at that distance. So L star over 4 pi d squared times the surface area of the dust that sees starlight. So that's pi a squared. And there's one last thing. Sorry, that should be a 2. We're going to multiply this also by Q absorbed. And this is the efficiency of the dust at absorbing light. So it's going to be some value between 0 and 1. It's just how good is it at absorbing starlight. So that's our P absorbed. Let me try to write this a little better. Sorry. Now we can write P emit, so the energy that the dust grain emits. We're going to assume the dust grain emits light over its entire surface, so the entire surface of the sphere. So that's going to be surface of a sphere is 4 pi radius squared. So 4 pi a squared. We're going to, again, throw in a kind of efficiency factor. So we're going to say Q emit, this is how good the dust is at emitting the energy it absorbs. And then multiply this by the flux from the dust grain, which flux is equal to sigma t to the 4th. So that's our Stephen-Boltzmann constant, sigma. So F equals sigma t to the 4th. This is the Stephen-Boltzmann law. Stephen-Boltzmann, sorry. So now we want to set these two things equal to each other and solve for t. So we're going to end up with 4, oh my gosh, that's going to be my pi, sorry. 4 pi a squared equals Q times Q emit times sigma t to the 4th. We're trying to solve for t, that's the temperature of our dust grain. And that's going to be equal to L star over 4 pi d squared times pi a squared times Q absorbed. Now, the nice thing is we can cancel out this a squared, this sigma, this pi a squared, and solve for t to get t to the 4th is equal to, we have divide by 4, so 16 L star over 16 pi d squared. And I'm almost out of space on my whiteboard, but we're going to make it work. Sigma, we divided by sigma, and then we're going to have this efficiency ratio. Oops, what happened? Q absorbed over Q emit. And then we can take the fourth root of both sides to get an actual temperature. So that's our little derivation for today, how we get a dust temperature. Assuming that our dust isn't rapidly rotating or doing anything else crazy, also assuming that our dust grain is spherical, isn't quite right. So this is kind of an approximate dust temperature if the dust grain is a certain distance away from a star or a star forming region that has a certain luminosity. Okay, so let me go back to sharing my PowerPoint so we can think about our other temperature. So our other temperature is the gas temperature. And this is going to be that energy, that kinetic energy of the gas. So we had the black body temperature in the dust. It has to do with how hot it is. And now we have a black kinetic energy temperature, a motion energy temperature for our gas. And this is going to be anywhere from 10 to 10 to the 6 Kelvin, depending on what ISM phase that you're in. Okay. So now that we know what temperature is, we can start thinking about what could change that temperature, either increasing by heating and increasing the temperature, or cooling and decreasing the temperature. And we're going to focus mostly, we're going to kind of switch back and forth between what temperature, but we're going to focus mostly on that gas temperature, that kinetic energy temperature when we think about heating and cooling. So the first thing that could heat up the ISM is supernova and shocks, the shocks from supernova mostly, but also other things moving through the ISM. Mostly supernova shocks though. So every time a supernova explodes, it inputs about 10 to the 51 ergs of energy into the ISM. So that's where we get this one FOE is 1 times 10 to the 51 ergs. So if you ever see the unit FOE, that's what it means. Not really used very often. So these supernova and their shocks will heat the warm and cold neutral medium as well as molecular clouds for the most part. And they will also blast highly energetic particles into the halo. So to show this in another way, supernova will cause something called supernova chimneys that will clear the area around them of gas and dust and blast highly energetic particles into the halo, which you can see here as well. And then the shocks from that explosion will travel through the ISM, heating it up. I really like this diagram here because you can kind of see spiral arms. Spiral arms are causing the giant molecular clouds to condense and start forming stars. Star formation regions are going to be in between the giant molecular clouds and where we would expect to see supernova, because you're forming the star forming regions out of the giant molecular clouds, and then eventually some of those O and B stars will go supernova as they travel around the disk. So we're kind of moving this direction from oldest young stars, exploding stars. So cool, life cycle of the ISM. We can also get heating of the ISM through cosmic rays. So cosmic rays are just atomic nuclei that have been accelerated to nearly the speed of light. So protons and electrons moving really fast. Possibly from ejections from supernova. So you could also kind of think of this as supernova heating the ISM. The lower energy cosmic rays heat the dense molecular cloud as well as some of the other phases, but primarily the dense molecular cloud. This image here is the disk of the Milky Way in gamma rays. So when these cosmic rays interact with other gases, you can produce gamma rays. So that's why it's our best way of kind of measuring the density of cosmic rays in the disk of the Milky Way. And just to kind of write this heating as a chemical equation, what it's going to look like is our cosmic ray, so our proton with a very high energy, is going to bump into a neutral hydrogen or a molecular hydrogen, some other gas in the disk. It's going to cause that gas to ionize, and it's also going to impart a lot of kinetic energy into the ionized proton and electron if it's a hydrogen or whatever else we're looking at. So we end up with 3 particles instead of 2, all of which are moving pretty fast instead of one thing moving incredibly fast. So this is imparted kinetic energy into the disk. We can also, of course, get heating from stars. So stars are blasting radiation of all kinds into the ISM, but a lot of UV, a lot of blue light is coming from stars. So that can heat up the ISM when it bumps into elements. So when we have photons from stars with a certain energy, if they bump into an element with enough energy to ionize that element, we'll end up with an ionized hydrogen, an ionized carbon, whatever this is, plus an electron that is carrying away some kinetic energy. So moving faster and heating up the ISM. So what I put here is that the energy of this electron is going to be equal to the difference between the ionization potential of this element minus the energy of the photon. So whatever is left over after you kick off the electron will be taken away in the form of kinetic energy, adding to the temperature, heating the ISM. So lastly, I wanted to talk a bit about dust heating because a lot of the free electrons that have energy in the ISM are coming from dust grains. So a lot of times we talk about dust heating in the ISM. So it's not that the dust are putting energy into the ISM, it's that starlight and supernova shocks are ionizing electrons from dust grains that then turn that radiation energy into kinetic energy and heat up the ISM. So in order to talk about dust, we first need to think about what the dust actually is. So we're going to break it up into 2 types, large grains and PAHs. And I also just wanted to briefly say here, this is a little bit complicated how you can actually calculate this, so I didn't want to go into it, but we can measure a dust to gas ratio as well to get an idea of how much dust and gas there is in a galaxy by looking at the ratio of the amount of absorption in the V band, which is going to be caused primarily by dust, and comparing that to the number of hydrogens along that line of sight. So between you and whatever you're seeing the absorption for, and that'll give you a dust to gas ratio. So this might be using like a 21 centimeter line to measure or something else, H alpha line. But we can use this, do a little bit of funky math to get a dust to gas ratio. For some reason, I was terrible and I gave you a gas to dust ratio. So if we just flip those, you can see that a gas to dust ratios are going to be around 130 in terms of mass, not in terms of number. So there's a lot more gas than there is dust because gases are going to be a lot lighter than dust. Gas particles are going to be a lot lighter than our dust particles. So in terms of number, there's a lot more gas than dust, but there are also, the dust particles do have a lot more electrons that could be photoionized and heat the ISM. So the first kind of dust I wanted to talk about was our large grains. So these are going to be dust grains, carbon silicate grains that are around a micron in size, so pretty small. This is an image of a dust grain from our solar system. So similar probably, but a little different. This is actually bigger than what we would expect in the ISM at 10 microns. But it's kind of the best we can do here on Earth, where we do have some dust particles that we've collected from this interplanetary space, but it's a bit harder to get into interstellar space and bring dust back. Then we have our PAHs, our polycyclic aromatic hydrocarbons. So these are long chains of hydrogens and carbon atoms. So here the darker particles represent the carbons, whereas the lighter particles are the hydrogens. And they are very efficient at heating the ISM because they have a large number of electrons that can be easily ionized. So when they're hit by UV light from stars, they can eject electrons or disassociate, break apart, And those different parts will carry kinetic energy into the gas, or those electrons will carry kinetic energy into the gas, heating things up. We're getting to cooling. So just another little equation here, a little bit of a way to think about why polycyclic aromatic hydrocarbons are so good at heating the ISM is to compare the photoelectric heating efficiency of both polycyclic aromatic hydrocarbons and grains. So that's what this eta is. It's the photoelectric heating efficiency. So how good are they at turning radiated energy, so light energy, into kinetic energy? And for PAHs, it's going to equal to, this is a fraction based on how much of the light from a star can actually get is high enough energy to eject electrons. And then here we can see this is the ratio of the energy that ends up ejected into the ISM, the kinetic energy of our electron, so and the energy of the light that was absorbed. So energy of the light that was absorbed minus the ionization potential of the PAH is going to be equal to the kinetic energy of the electron divided by the energy of the light absorbed. Tells you how much of that radiated energy, that radiation energy, was converted into kinetic energy heating the ISM. So how good is a PAH at increasing the temperature? Looks at how much energy is going to be turned into, radiation energy is going to be turned into kinetic energy. With grains, it's a little bit more complicated. We see that first we've got this Y, the yield, which has to do with how far light is going to have to penetrate into the dust before it hits an electron that it can ionize. It's a little complicated based on the size of the grain and also the path length of an FUV photon through the grain and the distance between electrons in the grain, but it generally works out to be about 0.1. So we've got this factor of 0.1 right out here in the start that's going to make everything a lot lower than you might hope for. And then again, we have something that looks kind of similar. This is going to be similar to our H nu minus IP, except now instead of ionization potential, this is a grain. We aren't really ionizing it. We're instead kicking an electron out. We're photo disassociating this grain. So instead of ionization potential, we have a work function, which is the energy needed to free an electron from a positively charged grain, minus the Coulombic, and also the Coulombic potential, this here, which is how hard is it going to be for this electron to escape a positively charged grain. And just because it's our PAHs, maybe there's some of these are already positively, some of these edges are already positively charged, but they're not all already positively charged. We don't have to worry about that Coulombic potential the same way we have to at the grain, where it does actually have to break out of what is a probably positively charged surface. So grains are just not as efficient at heating the ISM, but they are still a significant source of heating in the ISM. Lastly, I just wanted to show this to mention that most of the infrared, we often measure heating by looking at the infrared luminosity of a galaxy. And that's because most of the infrared luminosity, which is what I'm showing here, the infrared spectra of a galaxy, is dominated either by PAH features, so those features here, these kind of bumpy things, or hot dust, which is going to be here. So this is all essentially a black body curve from hot dust. Technically, it's a modified black body, but think of it like a black body. Okay, so if we're curious in photoelectric heating from dust, measuring in the infrared is going to give us a very good idea of what's happening there, because that has all of our PAH bending and twisting modes as they get as their electrons get photo ejected. So this is going to tell us how many PAH molecules there are, and this is going to tell us how hot the dust is. So how much light is the dust absorbing in the ISM? So adding this all together gives us a pretty good proxy for heating rates in the ISM. So now I'm going to talk a little bit about what can cool, because if we don't have something to cool, our ISM is just going to keep heating up and keep heating up and keep heating up, and we're going to get a feedback loop, and that's not going to be good. So we need something to take energy out of the ISM as well. So we need processes that convert kinetic energy, that temperature energy, into luminosity that can escape a galaxy through collisional processes. So these are going to be all processes that end up radiating really low energy light that's going to have a very easy time escaping the ISM. So if we're radiating optical light or UV light in a transition, it's not going to be a cooling process because that light is going to get reabsorbed, it's going to photo eject another electron, it's just going to go back into heating the ISM before it can escape. So pretty much all of our cooling processes are either going to radiate in the radio or in the far infrared. What does the cooling kind of depends on where you are. So if you're in a completely ionized gas, you're going to have a lot of free electrons and protons. So most of your cooling is going to be done through Bremsstrahlung emission, which is the free interactions of electrons. So as these electrons bump into each other, occasionally you'll get some of that kinetic energy converted into light that'll be carried away in the form of Bremsstrahlung radio emission. So that's if you're in a completely ionized gas. If you're in a partly ionized or mostly neutral gas, you're instead going to lose most of your energy through far infrared fine structure lines. And depending on where you are, what's colliding with those, what's exciting those lines is going to be different. So if you're in a partly ionized gas, it's mostly going to be through electron collisions with metals. The metals produce the far infrared fine structure lines. I'll talk about what those are in a second. If you're in a neutral gas, there aren't that many electrons left, so most of your cooling happens through hydrogen bumping into these metals. So the fine structure lines are any line that's produced by a spin flip. So similar to our 21 centimeter line in hydrogen, that's a hyperfine structure line because it's so long. I think the hyper comes from the fact that it's not in the infrared, it's actually in the microwave, I think, centimeter. Okay, but anything else with a spin transition is probably going to be one of these fine structure lines. So what this transition is showing here for the C+, what it means is we have this electron in the second energy level P shell is changing from a 1/2 spin to a 3/2 spin. More chemistry than I want to do, more quantum mechanics. So enough that it's a spin flip of singly ionized carbon, radiates at a wavelength of 158 microns, so very, very, very long, and it's a low energy transition. So temperature, kind of weird to think about it, the temperature of this transition is about 92 Kelvin. Which is, so some of the other lines that are going to be important are this 34.8 micron line of ionized silicon, and then the 205, so 204. The 205 and the 122 micron emission lines of singly ionized nitrogen, and then the 147 and the 63 micron lines of neutral oxygen. The last thing I just wanted to cover really quickly is that we can, similarly to how we looked at pressure equilibrium, we can think a little bit about thermal equilibrium. So for a thermally stable ISM, we need heating to balance cooling, so heating to equal cooling. Typically we write this, oh, I wrote this backwards too, didn't I? Sorry, as lambda is going to be equal to gamma. Lambda is our cooling, gamma is our heating. Sorry. Often also we'll look at that as a difference. So the difference between heating and cooling we hope is going to be 0 if we're pretty close to stable. We can also think of that as a difference in kinetic energy, which we can use the ideal gas law to say should be equal to NKT if N isn't changing, which probably not much. NKT, and then we're taking a derivative in time. So the only thing that's changing should be our temperature. So derivative with time. and these should be 0 if we're stable. And so this graph here is just showing essentially everything we discovered in one graph, where we've got heating lines, or lines representing heating sources and lines representing cooling sources. So the dashed lines are heating sources, got cosmic rays, just X-rays, and then photoelectric effect heating is most of the heating that's happening, but there's also some from cosmic rays and X-ray shocks from supernova. And then they also have, and then they show also the different cooling lines. So our C+ here, our neutral oxygen here, some neutral carbon lines if you get to really dense conditions. So in giant molecular clouds, you might have some neutral carbon lines as well. But essentially what we were just looking at. So hopefully if you're in a thermally stable stable state, we can add these up and we'll see that they're gonna mostly cancel. And what's doing the heating, what's doing the cooling is gonna depend on where you are in the ISM and what density you're at. So that was most of what I had for today. The last thing that everyone did was work through the Balancing Act Jupyter notebook, which has you look at some heating and cooling indicators in the galaxy's ice study and test to see whether or not things are staying relatively stable in these galaxies. See you next week for our question and answer session before the test.